Good morning, all. Let's move on with the next theorem. That's Millman's theorem. Uh, so this is rather fourth for you. We have covered three theorems: Thevenin's, Norton's, and superposition. Okay. The fourth theorem that we are seeing is Millman's theorem. Okay. This is simplest of the all. We have one more theorem, that is a maximum power transfer theorem. Okay. Uh, So that we will see later on. Today we shall see the Millman's theorem, the fourth one. Okay. What is the statement saying? Look at this. Everybody listen to this very carefully. If n generators of EMFs, understand, generators means here the voltage sources. Generator. EMFs means voltages. Understand that? Generators means the voltage sources. EMFs means the voltages that this particular generator is providing. Understand? So if n such generators of EMFs E1, E2 up to En, since there are n generators, they'll have EMFs E1, E2 up to En with internal impedances Z1, Z2 up to Zn. There are n generators with EMFs E1, E2 up to N and with internal impedances Z1, Z2 up to Zn are connected in parallel. Then if they are connected, if such n generators are connected in parallel, okay, then the EMFs and the impedances can be combined to give a single EMF E with internal impedance Z. Understand this? Suppose there are n generators, means n voltages it will give, and all those generators will have the n internal impedances. Okay, the generator with voltage E1 will have internal impedance Z1, generator with voltage E2 will have internal impedance Z2, and if such generators are connected in parallel, okay, then Millman says you can combine those to have one such. This is what he means. See, there are n generators, n number of generators, okay, with EMFs E1, E2, En respectively, having the internal impedance Z1, Z2 up to Zn respectively. If they're all connected in parallel, then this can be the EMFs and the impedances can be combined to give one single EMF E and one single internal impedance Z, where this E is E1 Y1 plus E2 Y2 up to plus En Yn divided by sum of all admittances. See, Y1 is admittance. If Z1 is there, Y1 is 1 by Z1. So it is E1 by Z1, E2 by Z2 up to En by Zn divided by 1 by Zn plus 1 by Z2 up to 1 by Zn. So instead of writing it in terms of the impedances, they have written the equation for EMF, the combined EMF, in terms of the admittances. Understand that? And the single impedance, the combined impedance Z is given by 1 by sum of all admittance. That means 1 by Z1 plus 1 by Z2 up to 1 by Zn. Okay, so you have to remember this particular equation for EMF and the internal impedance Z, the combined one. Okay, this is the combined EMF because of n generators. Okay, and this is combined internal impedance of the n generators. Okay, so what they mean is this. So if you have such a circuit, such n generators connected in parallel, then they can be combined to get just one generator like this, is what Millman's theorem is telling you, where E is given by the equation shown and Z is given by the equation shown. Okay, this we need to prove. Okay, so how we can prove that this particular parallel combination of n generators can be combined to give one generator of EMF E and internal impedance Z needs to be seen. Is everybody okay with that? What is Millman's telling you? Okay, what type of circuit is needed here? What type of circuit is needed for Millman's to be applicable? For Millman's to be applicable, there should be a voltage source in series with the impedance. and such a voltage source which is in series with the impedance should be in parallel with another such combination, should be in parallel with another such combination. That means let any number of such combinations be there, but at least there should be two combinations. Otherwise it is just this, otherwise if there is just one combination of voltage and the internal impedances, Millman's theorem is of no use. So if there are multiple such combinations in parallel, then Millman says you can combine them to make one E and Z. Okay, so for Millman's to be applicable, whatever is the circuit given, you have to bring the circuit to this particular form. If it is given in this particular form, it's fine, it is straightforward problem. Sometimes what they do is they will not be giving you the circuit in straightforward fashion like this. Okay, so in that case you need to bring the given network in this fashion, okay, before finding out the combined Z and combined EMF. Is that okay with you? Fine. So let's see the proof now. Note that Z1, Z2 up to Zn are internal impedances. Mind you, they're all internal. They're not physically connected is what is the meaning of that. They're not physically connected in series with these voltage sources. They are internal impedances is what you need to remember. Is that okay with you, everybody? Always the internal impedances or the resistances are connected in series. They are internally connected means they are series resistances or series impedances is what one should understand. Okay, but since they are playing role in the equation that we are obtaining, we have shown them outside. We have not shown them internally to the generator, but we have shown them outside. Okay, so internal impedances are the series impedances with the voltage sources. So that is what is being told in this particular statement. Fine. Now let's consider this particular combination, parallel combination of the generators, n number of generators. Okay. Can anybody tell me how many nodes are there? All are parallel branches. All are parallel branches. How many number of non-reference nodes are there? Anybody? Can you make out from this? Anybody, can you make an attempt? See, one node circuit, because these are all the branches in parallel, right? Okay, all are connected to the same point, all are connected to the same point. Okay, so that means the E that we are marking here, the node voltage, this is the node voltage. Now if I mark E means, okay, so everywhere here the voltage is E. Understand that it's the same point throughout. So the node voltage is E and this is ground. See here, this is ground which I am not marked. I should have marked that. When I'm dealing with node analysis, I should be marking it. Fine. See, if this is E, everywhere the node voltage is E. How many nodes are there? N number of nodes. No, we cannot say N number of nodes because all the nodes are same. Though we have got these points, see, all these points are connected, interconnected. Okay, so that means they're all same points. So how many nodes means I should not say N nodes. Okay, all N points are coming together at the same point, so it is just one node problem. So what is the voltage at that node? Because of this E marked here, the node voltage is E and this is ground. Fine. KCL we apply now. We have to apply KCL. How many branches are there? There are N number of branches. Okay, there are N number of branches. Fine. How many currents should be flowing? If N branches are there means we need to have N currents. Okay, after we say we have N currents, the question, next question that we need to be asking ourselves is how many among those N currents are entering and how many are leaving? Okay. Now, when can we say there is a current entering? We can say there is a current entering the node when there is a current source showing the current entering the node. Is there any such current source which is showing the current entering the node E? No. So that means there is no current entering, all the currents are leaving currents. That is the assumption we had made when we learned the node analysis for the first time. Okay, so whatever we have learned in module 1, that is what is we are going to apply throughout, whether it is node analysis or mesh analysis. So if you're good with the basics of mesh analysis, node analysis, source transformation, okay, you can solve any problem. Fine. So let's apply KCL at node E. Fine. What is the current in this particular branch, which is leaving node, which is leaving this node? What is this current? It is this voltage. E is the voltage. So E, that means here is also E, here is also E, here is also E. So E minus E1 divided by Z1 is this current. Okay. So E minus E2 divided by Z2 is this. Okay. Such n number of currents are there. Okay. The sum of all these leaving currents should give us 0 because there is no entering current. So that's why we get this equation. Is this okay with you, everybody? We have n branches, n currents, and all the currents are leaving the node. Is this okay with you? Now, let's separate E and E1, E2, E3s. That means let's just have a term separating this E. Let's bring this E in one term and all remaining EMFs in the other term. Let's try and make that now. This is the equation we have to go with. Okay. So what we are doing, I'm just separating the terms. I took E common. After you take E common, what is there with every E? 1 by Z1, 1 by Z2, 1 by Zn. So 1 by Z1 plus 1 by Z2 plus up to 1 by Zn are there here. And this minus E1 by Z1, minus E2 by Z2, minus En by Zn are all taken to the right hand side. That's why they become positive on the right hand side. Is this okay with you? We are just proving. What is that we are proving? They told, right? The combined EMF E is going to be this, or the combined impedance Z is going to be this. That we are proving. What is that we are proving? See, this equation we are trying to prove. This equation we are trying to prove. Fine. That's why we are doing this exercise. What did we do next? 1 by Z1 is there. What is inverse of the impedance? Inverse of the impedance is the admittance. Okay. Similarly here, inverse of the impedance is admittance. 1 by Z1 is Y1, 1 by Z2 is Y2. Similarly, 1 by Zn is Yn, and the same applies here also on the right hand side. Okay. So what is E? So E can be written as this right hand side, and this comes to the denominator of the right hand side. That's why we get our E to be this. Okay. So this is one proof that we have got the result for. Okay. E is this. Now we have to find out combined Z also. What do we need to do for that? Let's again consider the same circuit. Okay. So we have seen what is E going to be equal to. Now we need to see what is the combined Z because of these internal impedances are going to be. Since all the internal impedances are in parallel. See here, this, are they in parallel? If you ask, you will say no. You will say Z1, Z2, Zn are not in parallel. You will say. Why you will say they are not in parallel? Because I have shown them outside. I've shown them outside. Okay. For them to be parallel, they should have been connected like this here. They should have been connected like this here. But how do we find out the equivalent resistance or impedance across this? The Thevenin, suppose we are finding out Thevenin's impedance or resistance, or we are finding out Norton's resistance or Norton's impedance. What we used to do there? We used to deactivate the sources. Understand? So if you deactivate the sources, how is this going to look like? They're all becoming short circuit. So that means Z1, Z2, Zn will all be in parallel. Or in other words, since they are internal impedances, they would be in parallel. Okay, so that's why it is called, since all are internal impedances, they are parallel. Or you can say to find E, we can go for short circuiting this. If you are finding out the Thevenin's equivalent network, what is this network that we have obtained here? Let me show you that. What is this particular network called? There is a voltage source in series with the impedance. Yes or no? There is a voltage source in series with the impedance. That means this a Norton's network or a Thevenin's network? This is the Thevenin's network. In Thevenin's network, we have found out E. That means we have found out this open circuit voltage. This open circuit voltage. See, this is the voltage across the open circuit terminals. So this is open circuit voltage if you talk in terms of the Thevenin's voltage, Thevenin's theorem. Or if this is open circuit voltage, this has to be Thevenin's impedance. Since we are dealing with the impedances here, if you deal with impedance, it is Thevenin's impedance. If you deal with resistance, it is Thevenin's resistor. Is that okay with you? So if this is Thevenin's voltage, if this is equivalent to Thevenin's voltage, this will be equivalent to Thevenin's impedance. How to find out the Thevenin's impedance? By deactivating all the sources. So if you deactivate all the sources, what would happen? They would all come in parallel. Since they come in parallel, we can say the parallel combination of these impedances are going to be represented like this. Understand that? So what is Y? What is Y? Y is this? 1 by Z is Y. 1 by Z1 is Y1. 1 by Z2 is Y2. Then 1 by Zn is Yn. But what is that we want? We want Z. So we have Y. What is Z then? Z is inverse of this. Very simple stuff. But most of the people come and get stuck here. After this point, they'll not be able to prove this sometimes. Okay, so you need to, this in simple terms, you have to deal. 1 by Z is Y, 1 by Zn is Z1 is Y1. So you write this particular equation in terms of admittances, which is inverse of the impedance. Okay, then we need Z. Okay, so Z is what? Z is 1 by Y. What is 1 by Y? It is 1 by Y1 plus Y2 plus up to Yn. Is this understood? So this is quite a popular proof when it comes to Millman's theorem. Is that okay with you, everybody? So let's solve some problems on this. Very simple. This is the simplest of all the theorems that we are seeing. Fine. So let's move on with some problems. So here what they'll ask us to find out the Millman's equivalent circuit. What is Millman's equivalent circuit? It is actually Thevenin's equivalent circuit, but you're not supposed to go by finding out VOC and ISC by applying mesh analysis and node analysis. No, you're not doing that, but you're doing that by using these equations. Now, see what they're asking us. Find the current through 10 ohms by Millman's theorem. The same can be asked by Thevenin's theorem and Norton's theorem also. What do we do there? If you're asked to find out some current or voltage, what we used to do that? We used to remove the branch where that current is flowing or voltage is dropping. Okay, so the same applies here in Millman's theorem also, because we are asked to find out the current here. So what you would do, step one, you would remove this. So soon after you remove this, what you will be availing? You will be availing two open circuit terminals. Okay, so when you have two open circuit terminals, you have these parallel combinations. Voltage source in series with the resistance, voltage source in series with the resistance, voltage source in series with the resistance, and all these series combinations are in parallel. Okay, and that is where the Millman's theorem comes into picture. Fine, what I mean is this: remove 10K and mark the terminals as AB. Okay, and we are not comfortable to see this particular circuit like this. So what you would do? You would mark it this way. The same circuit is taken in this form. So whether the A is here or A is here or A is here, it's the same. Whether the B is here is B is here or B is here, it's all the same. Understand that? Okay, so that's why this particular circuit can be written in this form, which is the required format, with which we are very comfortable. This is not something that we're comfortable with. Okay, so this is something that we are used to, so we are comfortable with it. So let's write this particular circuit after removing 10K as this. Now Millman says this can be replaced by a single voltage source in series with single resistance or impedance. We could have written it as Z. We could have written it as V, not at all a problem. V, R, we could have written, okay, since they are all resistances. So Millman says, what is this? So let's see what is this. Now, one more thing that we need to be very careful with is, see, not all the polarities are same. See here, in the given problem, not all the polarities are same. It is plus minus, but it is minus plus. So this is where we need to be little careful about. Okay, so if you regard this as E1, if this is E1, E1 is plus 22, E2 is plus 48, E3 is minus 12. Understand that if this is E1, E2, E3, this is plus 22, plus 48, and this is minus 12. Is that okay with you? So let's be very careful regarding that. So let's find out E by using this equation. So this is the equation to find E. Okay, so just substitute. E is 22, Y is 1 by Z, and this is another problem. Okay, people think that this is the easiest. Yes, this is the easiest, but little care that you need to take when you are writing the exam or internals is suddenly people come and substitute this y1 as 5, y2 as 12, y3 as 4. No, but y1 is 1 by 5, y2 is 1 by 12, y3 is 1 by 4. Same here, 1 by 5 plus 1 by 12 plus 1 by 4. Understand? So that you need to be little careful about. Okay, everything is in detailed given. Okay, so if you just again listen this keeping the recorded videos, you will be able to learn this very well. Fine. See, what is that we need to look at? This E3 is minus 12. Very important. Fine. So what is E? E is 10.125 ohms. Get that? So we have to find out Z now. What is Z? Z is this. So we find out Z to be 1.875. So what did we do by finding out E and Z? We found out the Millman's equivalent circuit. Therefore, by Millman's theorem, we have obtained this. This is called as, you can call it as, we cannot call it as Millman's equivalent circuit, but this is Thevenin's equivalent, which we have obtained by Millman's theorem. So this Thevenin's theorem is connected to so many other theorems. Another theorem that I'm going to give you, okay, in the coming days is maximum power transfer theorem. Okay, so that maximum power transfer theorem is also connected to Thevenin's theorem. 80% of maximum power transfer theorem is Thevenin's theorem. Understand that? So if you are good with the Thevenin's theorem, you can understand this Millman's and maximum power transfer theorem very well. Okay, so it is as good as obtaining the Thevenin's network, but Thevenin's theorem, but we don't say that. Let's give the credit to Millman's here. Okay, because Millman's is the one who observed that maybe. Okay, that's why the name, the theorem is named after him. Fine. Okay, to find I, what we need to do, we need to connect those terminals again with 10 ohms. So after connecting 10 ohms, again the I will start flowing. Okay, and find out that I by Millman's theorem, that is by applying what? KVL. So I we have found out. This is how we do it. Okay, what is the thing that we have to be careful about is the change in polarity of EMFs or the voltages. Okay, so let's go on with the next problem. That is this. Find R such that the maximum power is delivered to the load, it is saying. Okay, so suddenly they are asking us the maximum power transfer theorem. So let's do this. Just a second. Using Millman's theorem, obtain one generator of EMF E and internal impedance Z across AB. So that means, so they have this, right? So let's remove this RL. Let's remove this RL. Okay. They are asking us to find out R. Let's do this by Millman's theorem. Okay. Find out this R such that the maximum power is transferred to the load. So what we shall do, we shall remove this. Okay, find out the Millman's equivalent circuit across AB. Fine. So what is that going to be? One is E1 here, one is E1. Okay, what is R1? R1 is R, Z1 is R, E2 is 2, Z1 is R again. So they're all Z1, Z2, Z3 are all same. Okay, so that's why it comes like this. Y1 is 1 by R, Y2 is 1 by R, Y3 is 1 by R, Y1, Y2, Y3 is 1 by R, 1 by R, 1 by R. Understand this point, everybody? Yes? Now, what would this E be? So this E is 2 volts. This E is 2 volts. Understand that? Now, what is Z? It is 1 by R plus 1 by R plus 1 by R. So it is what? R by 3. Get this point? So what did we obtain? We obtained the Thevenin's theorem equivalent, Thevenin's equivalent circuit. This is what we obtained just now. Understand this? We have got E to be 2 volts and Z to be R by 3 ohms. What is the question? Find out this R such that the maximum power delivered to the load is, what is that? 3 milliwatts. Find out this R such that when you find the maximum power transfer to the load is 3 milliwatts. That means they have given us the power, and for that power to be delivered, what needs to be our R is what we need to find out. So what we'll do here, this is our RT and this is our VT, as good as that. So therefore, by maximum power transfer theorem, they say, okay, what we can do. See, I'll just give you one hint here. Maximum power transfer theorem very well says that for maximum power to be transferred to the load, this I have not covered yet. I'm just giving you some hint regarding how the maximum power can be found out. Okay, for maximum power to be transferred, RL has to be RT. It is one example. Okay, so that's why what did we do? We connected this RL as R by 3. For maximum power to be transferred, what we need to do? They are saying we need to connect the load equal to the impedance that we have found out here. So that is when the maximum power would be transferred. Understand? So that we'll see in detail in the next theorem. But as of now, this can come as, they can sometimes club the theorems like this. Okay, so in such cases, we should be little smart to understand that if the maximum power has to be transferred to the load impedance should be equal to the impedance that we have found out by Millman's theorem or the Thevenin's resistance. Okay, so find out I by applying KVL, which happens to be 3 by R. What is power given by? Power is already given as 3 milliwatts, but what is power equal to? P max is given by I squared RL. So 3 milli is the power, I is 3 by R, okay, RL is R by 3. Okay, let me tell you one important thing. In the internals, you have made a mistake when you were asked to find out this power. If we are asking you to find out the power delivered by the voltage source, you cannot use this. If I'm asking you to find out the power delivered by current source, you cannot use this. You should use V into I only. When it is power delivered to the load, the resistance, then you can use this. Understand that? So it is going to be what? R is going to be 1 kilo ohm. So if you connect R to be 1 kilo ohm, then 3 milliwatts, the maximum power will be transferred to the load is what they are saying. Okay, let me just explain it again. What was the question? Find R such that maximum power delivered to the load is 3 milliwatts. So what did we do? We first found out, we just combined these resistances and impedance voltage sources, okay, to obtain what? Thevenin's equivalent network by Millman's theorem, which is this. See, which is this. This is as good as your Thevenin's network. And what they are asking, what RL, what R needs to be connected so that the maximum power is delivered to the load. Okay, so for maximum power to be delivered to the load that we connect here, the RL has to be this resistance that we have found out. Understand? That is what is told here by maximum power transfer system. That is what is told. Okay, that's why this is the only point we have to catch here extra. So if maximum power has to be obtained, then this RL, the load resistance, has to be this resistance. Okay, so that is why in the circuit that we have obtained by Millman's theorem is this, and what is the load that we are connecting is R by 3. Why did we do that? Because they already have given us the maximum power that is being delivered. 3 milliwatt is the maximum power. So since 3 milliwatt is the maximum power, okay, this has to be R by 3. Okay, that is why R is happening to be 1 kilo ohm. The meaning of this is, if you connect R equal to 1 kilo ohm in the given network, then the maximum power that is being transferred to load would be 3 milliwatts. Understand that, everybody? Okay, so that is what is told here. Therefore 1 kilo ohm resistor has to be connected as the load resistor for maximum power of 3 milliwatt to be delivered to the load, or R has to be that. What is the summary? For Millman's theorem to be applicable, the network has to contain multiple generators connected in parallel. Multiple generators means what? Voltage source in series with the impedance. One generator equivalent to EMF E and internal impedance Z obtained from multiple generators connected in parallel is actually Thevenin's equivalent. Whatever we do in Millman's theorem is actually obtaining the Thevenin's equivalent, is what they are saying. What we do, if there are many such parallel combinations, we obtain one E and one V, right? One E and one V, that actually is Thevenin's equivalent, is what this is telling. So Millman's theorem, Thevenin's theorem, and maximum power are interlinked. So we have not covered this, we'll be covering this, but they're all interlinked. Because Millman's equivalent, what we obtain is actually Thevenin's equivalent. Fine. And that is what is going to be part of the maximum power also, that we shall see in the coming class.